Welcome to part 2 of the lecture on machine independent optimizations. In the last lecture, we discussed the purpose of optimization, a couple of illustrations for optimizations. Today, we will continue with the illustrations, look at a few more optimizations. So, a quick recap, the purpose of machine independent code optimization is to remove the inefficiencies which are introduced by intermediate code generation. Well, it could be the improvement could be in the time domain, space domain or power consumption domain. It changes the structure of the programs sometimes beyond recognition, and it is a bunch of heuristics. So, there is no guarantee that there will be improvement, but there will be improvement whenever there is a possibility of doing so. The other important point is all the code optimizations actually are safe. In other words, they do not change the character of the program. Whatever the program was doing, it will continue to do so. The functionality of the program is definitely not changed. We looked at an optimization called unrolling a for loop last time. So, let us quickly go through it once more, because that is needed for the other types of unrolling as well. Here is a for loop with here is a for loop I equal to 0, I less than n and I plus plus, with the two statements S1 and S2. The I inside parenthesis indicates that this is the ith instance of the loop iteration. So, in each iteration it is a different statement as such, instantiation of the statement. When we want to unroll the loop, let us say 3 times, S1 and S2 will be repeated 3 times. So, it is indicated as S1I plus 1 and S1I plus 2, similarly S2I plus 1 and S2I plus 2. Why do we want to unroll a loop? The primary purpose of unrolling a loop is to make the body of the loop much larger. Perhaps it is needed to reduce the overheads of parallel execution, as we will see very soon. So, perhaps for instruction scheduling, the body of the loop must be much larger and so on and so forth. So, in this case, the loop will again start from 0, but it will not run as many times as the old one, that is the n part. So, here we always check I plus 3 less than n, and we increment I by 3. So, it is really approximately n by 3 number of times that the loop really runs. Then at the end of it, suppose n minus 1 is not a multiple of 3, right. So, suppose n is 6, then n minus 1 is 5 and it is not a multiple of 3. So, to begin with I equal to 0, the unrolled loop runs once. So, then I is incremented by 3. So, I becomes 3. So, and then it now the problem is I plus. So, now 3, 4 and 5 they are actually many few more than what is needed. So, this part of the loop comes into play. So, here we begin with k equal to I, that is 3, and then we are going to run 3, 4 etc. In this part of the loop and complete the rest of it. So, otherwise some of the iterations may be left out, that is the major problem here. Unrolling while and repeat loops is similar. For example, we have while C S1 S2. So, 2 statements in a while loop and repeat S1 S2 until C is the repeat loop. So, if the while loop is unrolled, then again let us say 3 times, we have 3 instances of S1 and S2 here. The only problem here is we do not know whether the condition C will hold true after one iteration, 2 or 3 iterations. So, after every set of our set of statements S1 and S2, we need to introduce a break, a conditional break. So, if the condition C is false, then you really get out of the loop and stop the loop. We should not be executing these two. So, if it is true, then we come here, S1 and S2 is executed again, and you check again. So, these two checks are necessary to make sure that these two instances are not executed unnecessarily. It is exactly the other way here. Repeat until loop executes at least once. So, we execute. So, here at least once does not hold. So, the C is checked right here the first time, and if it is false, we do not execute the loop at all. So, that is already taken care of by the while condition here. Here S1 and S2 will be executed, that is the at least once part, and then you check it, the S1 S2 goes on executing until the condition C is true, and once it is true, it stops execution of the loop. So, instead of checking not C as in this previous case, we check whether C is true. If C, then break. Similarly, S1 S2, and then if C, then break S1 S2 and until C. So, this is unrolling the while and repeat until loops 3 times, very similar to the for loop, but there are conditional breaks in between. The next purpose, the next optimization that we are going to consider is the function inlining. So, let us take a very simple function, find greater int a10 comma int n. So, this is supposed to traverse the entire array A, check whether there is an element a I greater than n, and if so, return that index, a very simple function. What does inlining this function imply? Inlining this function implies that whenever there is a call, x equal to say find greater y comma 250, there will be no subroutine jump executed, but this particular statement will be this find greater function call will be replaced by really the body of this particular function with some renaming of variables. Why should we do this? This is really going to make the execution much faster, because the overheads of subroutine jump and subroutine return or and creation of the activation record etc., are all eliminated. So, let us see how it works. So, let us say the call is x equal to find greater y comma 250, array is y and n is 250. So, in the place of the I that we have here, we have declared a new I, and in the place of this array A, we have a new array called new A. We begin with new A equal to y. So, and then you iterate. So, new I equal to 0, new I less than 10 and new I plus plus. So, this is the replacement for the I variable that is here, and the check y a I greater than n will be new A with new I greater than this n, which is 250, and if so, we just assign x equal to new I, that is we are executing the return statement now, and then go to exit, jump out of the body. So, there is no question of subroutine jump and subroutine return, but the value that is necessary will indeed be returned by this particular statement. The advantage here is as I said, the overheads are much lesser, and the disadvantage is in the place of one subroutine call, we now have a complete body of the subroutine call, that is the code itself. So, if there are 10 places where this subroutine is function or procedure is called, we would have 10 pieces of this code instantiated in those places. So, the code has really blown up, and if you inline every function in the program, the code size could become impossible to manage, unmanageable. Now, therefore, compilers provide directives to say whether some code should be inlined or should not be inlined, and based on that inlining of the functions and procedures happens. The other point is it is not possible to unroll or inline recursive functions and recursive procedures. We really do not know how long that procedure will run, and that may depend on some value which is not known at compile time. So, inlining of recursive functions is not possible. And now we come to the next optimization called tail recursion removal. Just now I said the recursion cannot be removed. So, I am not contradicting myself when we say it is possible to remove tail recursion. So, let us understand what is tail recursion first. So, here you have a function called sum, a very simple one, which takes an array A as a parameter, an integer called n and a pointer to integer called x, int star x. So, the body is if n equal to 0, then star x equal to star x plus a 0. So, it is actually assuming that the star x has been initialized to some particular value. So, now this function is supposed to sum up all the value all the elements of the array A. So, if n is 0, the 0th element is put into star x, otherwise star x equal to star x plus a n, and then sum is called again with n minus 1 as the parameter and the same x. So, as we go on with the smaller and smaller values of n, this will be n minus 1, n minus 2, etc., etc. Eventually, it becomes a 0 and the recursion terminates here. This is called a tail recursive function simply because the recursive function call is the last executable statement in the body of the function. So, please see here, this then part has no recursion at all, and in the else part there is an assignment statement and then there is a sum call. Such a recursive statement a procedure is called a tail recursive procedure, and it is possible to convert such a tail recursive function or procedure to a while loop, and that is called removal of tail recursion. So, let us see what is happening. We have the same function declaration as before, int a, int n and int star x, and instead of the recursion we simply have while true, and then first part is the same. If n equal to 0, star x equal to star x plus a 0, and then get out of the while loop with a break, because this is where the recursion terminates. So, that is what we are doing here as well. Otherwise, so we are now looking at this body, star x equal to star x plus a n remains the same. Instead of calling the function sum with a n minus 1 x, we do n equal to n minus 1 and then say continue. So, the while loop continues, and the execution of the body of the while loop also continues. It terminates when n equal to 0. So, this is the translation of the tail recursive procedure to a while loop, and this will work only if the function or procedure is tail recursive, and it will not work in general recursion, in the case of general recursion. Vectorization and concurrentization, this is another optimization which is possible. We are going to study this in some detail later on. Let us say we have a simple for loop I equal to 1 to 100 do x I equal to x I plus y I. It is easy to see that every value of I, for every value of I, the array element which is accessed, that of x and y, they are different. So, in I equal to 1 it is x 1 equal to x 1 plus y 1, with I equal to 2 it is x 2 plus y 2, x 2 equal to x 2 plus y 2, and so on and so forth. So, it is possible to run every iteration of this particular loop in parallel. So, in a vector computer it is possible to execute all these statements, let us say 100 of them, in vector mode. So, there is a vector of so this entire array x is accessed once into a vector register, the entire array y is accessed once into the vector register of size 100. So, there will be 100 additions which happen at the same time with the corresponding elements of x and y taken, and this assignment is also a vector assignment which assigns it back to the variable x, which would be in a vector register. And if it is a parallel multi-core type of machine, then every iteration will be run in parallel mode. So, that is why the indication is for all I equal to 1 to 100. So, iteration 1, 2, 3 etcetera will run on let us say 100 cores of the multi-core machine, each one of them executing single assignment, but with a different I. So, that completes the purpose of this for all loop. So, you can execute them in parallel. Let us look at another example of vectorization to see what is not possible. Here we have again a very simple loop, but with a small change. Instead of x I equal to x I plus y I, we have x I plus 1 equal to x I plus y I. This is not a parallelizable loop. The reason is let us expand the loop. So, take I equal to 1. So, we get x 2 equal to x 1 plus y 1. Take I equal to 2, we get x 3 equal to x 2 plus y 2, then x 4 equal to x 3 plus y 3 etcetera. The x 2 which was computed in I equal to 1 is used in I equal to 2, x 3 which was computed with I equal to 2 is used in I equal to 3. So, every value which is computed in iteration I is used in the iteration I plus 1. So, because of this, it is not possible to run the iterations in vector or parallel mode independently. They have to be run in a particular sequential order as indicated by the for loop. So, this loop is not parallelizable and it is not vectorizable either. So, we are going to study later conditions for vectorization, conditions for parallelization, how to actually modify the loop, so that these conditions are modified and so on and so forth. Then there is a transformation called loop interchange. Let us look at this particular loop I equal to 1 to n, j equal to 1 to n, a I plus 1 comma j is a I j star b I j plus c I j. In this case, the outer loop is not parallelizable. You will have to take my word for it for this particular thing, because it is not possible to demonstrate how it is so with the machinery, technical machinery that we already know. We need to learn about dependencies, which we are going to do a little later. So, let us assume that the outer loop is not parallelizable, but the inner loop is definitely parallelizable. But then if you actually parallelize just the inner loop and run the outer loop in sequential mode, then the each one of the inner loop statements will be run in parallel mode. So, the work is actually very small for each iteration. So, in a parallelizable loop, the cores must get as much work as possible in each for each thread that runs on the core. So, what we really do is interchange these two loops. The j loop goes outside and the I loop comes inside. So, now we have j equal to 1 to n and I equal to 1 to n. Now, the outer loop is parallelizable and the inner loop is not. So, we are going to run the inner loop in sequential mode and run the outer loop in parallel mode. So, for each iteration we create a thread and that thread will actually execute this entire for loop. There is a lot more work in this case per thread, because this entire loop is executed for each thread for each iteration of j. So, this is a much more beneficial case for us. The overheads of parallel execution are going to be small, because the work inside the thread is quite large. So, we are going to employ such in loop interchange whenever necessary during parallelization. The last optimization that we are going to see, an illustration of which is here, is called loop blocking. So, here is a small loop I equal to 0, I less than n, I plus plus, and j equal to 0, j less than m and j plus plus. So, the loop is a j I equal to b I plus c I. If this loop is run as it is, it may so happen that because of the large sizes of n and m, the cache misses, the n and m may be much larger than the cache size of the machine. So, the every time we execute this, there may be a number of cache misses. So, the speed of the loop will become very less. So, what we can try to do is divide these two loops into smaller loops. So, instead of 2 loops, now we have 4 loops. The outer 2 loops run with with an increment of 64 each. I equal to 0, I less than n, I is equal to I plus 64, and similarly J equal to 0, J less than m, and J equal to J plus 64. But the original I and j loops now run from 0 to 63, rather I to 63. So, first time it is 0 to 63, second time it will be 64 to 127, and so on and so forth. Similarly, J will also run from J to J plus 64. So, now what happens is because of this small size 64, this is not a magic number, it is just that this 64 will be the size of the cache line in a particular processor. It could vary from processor to processor. So, if that happens, then this entire the inner loop now iterates on J. So, we are going to modify C j very quickly, but B I will not be modified so quickly. So, this entire C j may fit into a cache line. So, there will be only hits from then onwards, and similarly the entire B may fit into a cache line. So, we are going to actually keep them, the B part will remain in cache for a very long time. This C part, every 64 numbers will be evicted, and in the next iteration 64 new numbers will be placed in the cache, and so on. So, every time we get the 64 numbers, they will be used immediately. Number of cache hits will be very large, and therefore, this is a much more efficient scheme compared to the previous one. So, we will this is the end of this particular lecture on introduction to optimizations. So, now we are going to continue with the next one called data flow analysis. So, welcome to the lecture on data flow analysis. So, what is data flow analysis? You see, we saw many examples of optimizations so far, and we are yet to see how exactly these optimizations can be performed inside a compiler. We need to actually compute a lot of information in that is available in the program, take it inside the compiler, and then the information will be used by the compiler in order to perform the optimizations. That is how it goes. Collection of information by the compiler by analyzing the program, traversing the program, is called data flow analysis. So, these are techniques that derive information about the flow of data from program execution paths, along program execution paths. So, what is a path in a program? Well, you have a beginning for the program and end for the program. Let us just assume one function or one main program. So, you start from a point P1, an execution path from point P1 to Pn is a sequence of points P1 to Pn such that for each I, Pi is the point immediately preceding a statement and Pi plus 1 is the point immediately following the same statement, or Pi is the end of some block and Pi plus 1 is the beginning of a successor block. In other words, the program begins execution, it follows a particular sequence, executes a particular sequence of instructions. So, between each of these instructions is a point, and if you actually connect all these points, so we will be able to collect information by traversing these paths P1 to Pn. In general, there is an infinite number of paths through a program, and there is no bound on the length of a path. So, it is not possible to actually execute all the paths in the program and then collect information. It is just not possible to do that. Whereas program analysis summarize all possible program states that can occur at a point in the program with a finite set of facts. So, this is a very important point. At any point in the program, we are actually going to only store summary information. So, there will be large number of program states that are possible at a point. Perhaps if the program can run in continuously without termination, there will be an infinite number of states. If the program is going to terminate in a certain amount of time, then the number of possible states is not infinite, it is finite, but it is still extraordinarily large. Therefore, this summarization is a very important point, and we will see how it is done. And no analysis is necessarily a perfect representation of the state. So, it does not matter which analysis we are actually doing, every one of these is in some sense going to create a loss of information. Nothing is a perfect representation, and this is the conservative nature of the analysis. What are the uses of data flow analysis? So, data flow analysis information is used for program optimizations, of course. I have given you plenty of examples so far: constant propagation, copy propagation, etc., etc. And it is also useful for program debugging purposes. For example, which are the definitions of variables that may reach a program point? These are what are known as reaching definitions. So, we may want to compute the reaching definitions and then use it in program debugging. So, let us see what exactly is a data flow analysis schema. Before that, we need to understand what is a data flow value. So, a data flow value for a program represents an abstraction of the set of all program states that can be observed for that particular point. The set of all possible data flow values is the domain for the application under consideration. So, the point is the data flow value itself is an abstraction, and the set of all data flow values is the domain. Let us take a simple example. For the reaching definitions problem, let us say we are going to define this as the first data flow analysis problem very soon. The domain of data flow values happens to be the set of all subsets of definitions in the program. So, in other words, if there are 10 definitions, we are going to consider the subsets of all the 10 definitions in the program. There will be 2 to the power 10 subsets possible, and each one of these is a possible data flow value. So, this is the abstraction that we are looking at. Why is it this is important? We will see very soon. Each data flow value will possibly be an estimate of the information that reaches a particular point. Then we should also know what is in S and out S as notation. These are data flow values just before and just after the statement S. And data flow, so if we are looking at basic blocks, this becomes in B and out B. So, in B is the data flow value before the basic block is entered, and out B is the data flow values just after the basic block is completed. So, the data flow problem itself is to find a solution to a set of constraints on in S and out S for all the statements S. So, for us it may become the basic block in B and in B. So, we will be looking at constraints on in B and out B. Continuing with the data flow analysis schema. So, we have now we are yet to see what the constraints are. There are two types of constraints possible. One, those based on the semantics of the statements. So, how exactly the statements in the program modify the data flow values. So, these are transfer functions and those based on the control flow. So, the control flow may change because of the conditions becoming true or false. So, thereby the data flow will also change. Those is another set of constraints. And now we are ready to define informally what a data flow analysis schema is. It consists of a control flow graph, a direction of data flow either forward or backward. This will be clear only when we see an example. A set of data flow values. So, this we already know, a set of values is the domain. A confluence operator. So, normally set union or set intersection operation, and then we have transfer functions for each of the blocks. So, these are the 5 entities in our data flow analysis schema. And another important point is we always compute what are known as safe estimates of data flow values. So, what is safe about them? A decision is or estimate is safe or conservative if it never leads to a change in what the program computes after the change. So, these safe values may be either subsets or supersets of actual values based on the application. So, it is difficult to say define this safe estimate without looking at a particular application. So, the only thing we can say is it never leads to a change in what the program computes, and therefore, we will see what safety means as we take up each particular example of data flow analysis. The first problem is the reaching definitions problem. So, before we define the what exactly we mean by a definition D reaches a point, we need to understand what we mean by killing a definition. So, we kill a definition of a variable if between 2 points along the path, that is we have a definition of a variable and then we have a path starting from that particular definition and it is going on and on. So, along that path pick up any 2 points and between these 2 points there is an assignment to A. So, the previous definition is not valid anymore, there is a new value assigned to A. So, the new value will now be available along that path from now on. So, this new assignment of A kills the old assignment or old definition of the variable A. A definition D reaches a point P if there is a path from the point immediately following the definition D to P, the point P, such that D is not killed along that path. So, this is what we mean by a reaching definition. So, for a particular point there may be many definitions which reach that point and are not killed along the path of their along which they reach the point. So, let us take a simple example and understand what we mean by unambiguous and ambiguous definitions of a variable. Here is an example assignment called which is A equal to B plus C. This does not involve any pointers, they are all ordinary variables. So, this is called as an unambiguous definition of A. So, there is a definition attached to the A. And later on, let us say there is another assignment star p equal to D. This is called ambiguous definition of A, because this pointer p may point to A, it may point to other variables also. It is not certain during compilation whether p what exactly p points to, it may be A, it may be a few others also. In fact, sometimes we may not know what p points to at all, unless some kind of pointer analysis has been conducted. Assuming that we have done some pointer analysis, it is still not going to be possible for us to say precisely what p points to at this point in the during the execution. We can only say, well, p will possibly point to A, B, C, that is all. Which one of these we do not know. Therefore, because we are not certain that this is an assignment to A, it could be an assignment, it need not be also. We will say this ambiguous definition will not kill the previous unambiguous definition, whereas sometime along the same path from this to onwards we had another assignment A equal to k minus 1. This assignment has ordinary variables. So, this is a new definition of A, and this will definitely kill the old definition of A here. Okay. So, this is how we understand killing of definitions and what ambiguous definitions do. So, for the reaching definitions problem, we compute supersets of definitions as safe values. In other words, it is safe to assume that a definition reaches a point even if it does not, it is not going to harm us. The application of this will be such that this will not harm the application. So, if we had assumed that if we do not know whether it reaches or not, then let us not say it reaches. So, suppose we said that, then we may be actually harming the application. So, that is why the conservative or safe estimate of a data flow value at any point will depend on the application. So, let us take the following simple example: A equal to 2 and A equal to 4, we assume that both of them reach the point after the completion, complete if then else statement is over. That is, you have A equal to B, A equal to 2, else if A equal to B, A equal to 4. This is the completion point of the if then else statement. So, we are going to assume that A equal to 2 and A equal to 4 reach this point, both of them. But if you look at it very closely, suppose A was equal to B, then A equal to 2 would have been executed and the else part would have been skipped. In that case, A equal to 4 would never have been executed. Suppose A equal to B was false, in that case we are again checking whether A equal to B, which is again false. So, A equal to 4 is not executed in the else clause also. So, in other words, A equal to 4, this definition, that is the value of 4 in A will never reach this point, but we have no idea of what the values of A and B are. We have not tried to actually interpret these values as we go along. So, in case of if then else of this kind, we are going to assume that A equal to 2 and A equal to 4 both of them reach here, but in reality only A equal to 2 possibly reaches this point. So, this is the conservative estimate, and since we do not know the values of A and B, we said both of them will reach even though one of them reaches. Now, we come to the heart of the problem formulation. All the data flow constraints are normally written as equations. So, here we have two equations, one for in B, other one for out B, and some initialization. So, let us look at the syntax of the equation. It states in of B, B is a basic block, in of B is the set of values which reach the beginning of a basic block, is the union of out P, where P is a predecessor of the basic block B. So, in other words, once we let us take this example. So, here you have a basic block B 1, this is the in point of the basic block, this is the out point of the basic block. So, similarly here is in of B 2 and out of B 2. So, what this says is in of B is a union of the out sets of all the predecessors of B. So, let us take this B 2, this has B 1 as one of the predecessors and B 4 as the other predecessor. So, when we compute the in set for B 2, we are going to take the out sets of these two and then make a union out of them. So, that is what this really says. So, this union operator which is present here is called as the confluence operator, and this could be intersection. Okay. It is possible that this is intersection. The set out B, the equation is written as gen of B unioned with in B minus kill B. So, here the equation is written as out B equal to this gen B and kill B are constants, they are computed before the data flow analysis problem is solved. They are not actually computed during the execution of the problem. So, they are constants. In B is a variable. So, out B is really a function of in B. In such a case, we first compute the this value in and then we compute the value out. Okay. So, this type of a problem where out is a function of in is called as a forward flow data flow analysis problem. So, here we have a confluence operator union and a forward flow analysis in this particular example. Now, let us understand what gen B and kill B are. Gen B is the set of all definitions inside the basic block B that are visible immediately after the block, that is downwards exposed definitions. So, let us understand this with the example. Here is the basic block B 1. There are 3 definitions D 1, D 2, D 3 in this particular basic block. So, we are looking at this particular point when we compute gen B. So, D 1 assigns a value to I, D 2 assigns a value to j and D 3 assigns a value to a. At this point, all these 3 definitions are valid because none of them have been superseded by any other definitions. So, for example, we had in the same block, we suppose we had D 4 I equal to some k minus 1. In such a case, D 1 would have been killed by D 4, it was not have been the value defined by the definition D 1 would not have been visible after D 4. So, the gen B at this point would not have contained D 1, whereas in this case this is not so. All the 3 definitions are visible at this point, their values, the values they compute are all valid at this point. So, gen of B 1 is D 1 comma D 2 comma D 3. Now, things are very similar in B 2. It defines I and j, D 4 and D 5 and they are still valid at the exit point of B 2. So, gen of B 2 is D 4 and D 5. Gen of B 3 similarly is D 6, there is only one definition and there is no question of superseding it, and gen of B 4 is D 7, again only one definition. Kill B, there is a small problem which is interesting. It is the union of the definitions in all the basic blocks in the flow graph that are killed by individual statements in B. So, that is we are going to look at let us say this particular block B 2, okay. It defines I and defines j. we will say that the kill set for B2 consists of all the statements in the other blocks B1, B3 and B4, which actually define I. Okay. So, for D5 similarly, we are going to consider all the statements in B1, B3 and B4 which define J. So, this I will actually kill D1, it will not allow this particular value to go through the basic block, that is what we mean by killing. Similarly, the value of I defined by D7 will not be allowed to go through this particular block, because there is a new definition of I here D4. It is irrelevant whether control can actually reach this point at all, it just does not matter to us. The reason is, we are going to compute kill a set of a particular basic block as an over approximation. There will be some elements in it which are not relevant, but they are not harmful to us. If we want to compute the kill set of a basic block exactly, the set of statements which is actually killed by that basic block, then we should actually solve the reaching definitions problem and then go back and compute the kill set. So, this is like having the chicken before the egg. So, we would like the kill set to be available for computing the data flow values, and we cannot be spending we cannot say that we will have to solve the problem of reaching definitions to get the computation to compute the value of kill. So, we actually over approximate kill as the union of the definitions in all the basic blocks, whether there is a control flow possible from that basic block to B at all is irrelevant. We are not even going to check it. We just take all those which are definitions which are killed by individual statements in B, put them in a set, and that is our kill set. So, here for example, is a nice illustration of what I just now said. See, D1 defines I, and it is not possible for the definitions D4 and D7 to enter the basic block B1 at all, because from B1 once we go out, we will not be able to come back to B1. But still the kill set of B1 will contain D4 and D7 of course, and corresponding to J it will contain D5, and corresponding to A it will contain D6. So, all these are in the kill set. So, this is the over approximation I really meant. So, in reality this would have been really phi, nothing at all. These definitions cannot kill anything. Okay. So, now for this particular block kill B2, so D4 kills D1, D4 kills D7, and then D5 kills D2. So, that is why the kill set is here. For the basic block B3, the kill set is just D3, because there is only one definition of A that is available here, that is in basic block B1. And for B4 it is D1 and D4, because these are the only two definitions of I in the other two blocks. So, now this is pass 1. So, now we have computed gen, we have computed kill. So, let us understand the meaning of these two equations. The outset says, out of B says, whatever is computed in the basic block, that is gen, the local computation, locally generated set of definitions, and then union it with whatever comes from the top as in, and whatever is killed by the basic block, that is removed minus kill. So, if you look at this, suppose we take the basic block B2 and we are computing this outset. Okay. So, we are computing this. So, whatever is generated by the basic block B2 will definitely be visible at this point. These are definitely the definitions which reach this particular point, the exit point of basic block B2. Then there will be some definitions which will be reaching this point, that is the in set, right. And then these statements which are reaching here, some of them will be killed because of these statements here, right. So, we have to remove the killed part from that, and that will give us the outset. Okay. So, if we do that here, the initialization is in of B 2 equal to 5 for all basic blocks. Please see that in of B 1 is 5, B 2 is 5, B 3 is 5 and B 4 is 5. So, here it is very simple, out B 1 is D 1, D 2, D 3, this is 5. So, nothing can be taken out of 5. So, in the first pass out of B 2 will be just gen of B 2, okay, and out of B 3 is gen of B 3, out of B 4 is gen of B 4. Let us look at the second pass. So, in the first pass the computation is over. So, now here, now we need to compute the inset for the second pass, okay, using these values of outsets. So, for this particular thing there is nothing, no special possibility, nothing gets modified, in B 1 remains 5, nothing comes in here, but for this the outset of B 1 is D 1, D 2, D 3, outset of B 4 is D 7. So, these are the two non-empty sets which are coming along these two paths. So, we need to take the union of these two, because all the definitions which come here along this path also reach this point, all the definitions which come along this path also reach this particular point. So, for out of B 2, we actually the next time we are actually going to take this out of in of B 2, we are going to take out of B 1 which is D 1, D 2, D 3, we are going to take out of B 4 that is D 7 and put them inside in of B 2, D 1, D 2, D 3, D 7. Okay. So, similarly, if you look at the inset of this, there is only one arc here. So, outset of B 2 will become the inset of B 3 in the next pass. Okay. So, that is here. Then similarly, there is only one, there are two arcs coming in here. So, we are going to take the outset of B 3 that is D 6 and the outset of B 2 that is D 4, D 5, take the union of these D 4, D 5, D 6 will be the the inset for B 4. So, this computation actually has to be carried out a number of times. So, we compute start with we compute gen and kill once for all, we initialize in B 1 to 5 in B 2 of this thing and 5 and so on. In the first iteration we compute out of B 1, out of B 2 etc. In the second iteration we compute again in and out. So, third iteration we again compute in and out based on the values which we computed before. So, this set of iterations goes on until none of the values change. So, here for example, once we reach this set of values, out B 1 is D 1, D 2, D 3, out B 2 is D 3, D 4, D 5, D 6 etc., etc. Okay. So, these are the various definitions which each is where we can just verify once. At this point for example, out B 2 says D 3, D 4, D 5, D 6. So, D 3 takes this path and it is A. So, A is not modified here. So, it reaches this point. D 4 and D 5 of course reach this particular point, and how does D 6 reach? So, D 6 is here, it goes out, comes here and travels along the loop edge, enters this point and comes out again. So, that is how D 3, D 4, D 5 and D 6 reach this particular point. So, and if you take this point, it is again D 3, D 5, D 6, D 7. So, D 3 takes this part and enters this point, D 6 takes this path and enters this particular block and goes out, and then D 5 comes here. What you should observe is D 4 does not come here, nor does D 1. The reason is there is a new definition of I here, this kills D 4 and D 1. So, this D 7 supersedes D 4 and D 1, and therefore, they can actually never come to this particular point, they can never reach this point. Okay. Whereas, this is different, there is only one difference. So, it reaches this point. Once these values are computed in the next pass, there is no change of values at all. This is the final iteration. Okay. So, Now, this is the iterative algorithm for computing reaching definitions. This is what I was saying. You have initialization in b equal to phi, out b equal to gen b, then change is set to true, and you go on until actually change remains true. Okay. So, first set change equal to false, then compute the two equations in b equal to and out b equal to. If and the old value of out is not same as the new value of out, then change equal to true. So, we have to iterate once more. Once out be equal to old out, change has false. So, we do not change set change equal to true and then we come out. So, until none of these blocks change, we need to iterate, and once all of them until the blocks keep changing, we need to iterate, and once none of them change, we come out. So, these are all this is the way the algorithm computes these values. So, gen, kill, in and out sets are all represented as bit vectors with 1 bit for each of the definitions in the flow graph. So, all these values of union operations of union, minus, etcetera become bit vector operations. So, we will I will explain this again in the next lecture, and this is the end of today's lecture. Thank you.